Okay, so we're going to prove Stewart's theorem, which states that for the figure below, right, for this figure, ct squared plus xyc is equal to xa squared plus yb squared. So what my strategy is I'm going to start on the right-hand side of this equation and try to get to the left-hand side. Okay, and the way I'm going to go about this is I'm going to find a squared using the law of cosines for this triangle here, and find b squared using the law of cosines for this triangle here. Okay, so let's go ahead and get started. So we'll start with proof. Okay, so let me scoot down a little bit. By law of cosines, right? I know that a squared is equal to t squared plus y squared minus 2 ty cosine of, and I need an angle. I need this angle here that corresponds with that A for this triangle here. I'm just going to give this angle a measure of alpha. So it'll be cosine alpha. Okay, so of course I want xa squared. So what I'm going to do is I'm going to multiply both sides of this equation by x to get my xa squared. So xa squared is equal to t squared, xt squared, right? Plus xy squared minus 2tx cosine, 2txy cosine of alpha, right? Okay, so this is an important one. So I'm going to put a star next to it. Now I want yb squared, right? So to find b squared, I can use this triangle here, right? So looking at that triangle, I know by law of cosine that b squared is equal to x or t squared. Let me go ahead and put t squared. T squared plus x squared minus 2tx cosine of. So if this angle here is alpha, that means by linear pairs, the property of linear pairs, the measure of this angle is 180 minus alpha, right? So this will be 180 minus alpha. Now we have a special property for cosine of 180 minus alpha. We know that's the same thing as b squared is equal to t squared plus x squared minus 2tx times negative cosine of alpha. Remember, cosine of 180 minus alpha is the same thing as negative cosine of alpha. Okay, so finally, this implies that b squared is equal to t squared plus x squared. Now, negative 2tx times negative cosine alpha will be positive 2tx cosine of alpha. Now, of course, remember I want to multiply that by y. So this implies yb squared is equal to yt squared plus yx squared plus 2txy cosine of alpha. And this is the other important equation. Now, for my equation, I want to add those two together and hopefully reduce it to this, right? So I'm going to do xa squared plus yb squared. So here's my xa squared up here. Let me scoot it up a little bit. So xa squared plus yb squared is going to be x t squared plus y t squared plus x y squared plus y x squared. And notice what happens. This is negative 2txy cosine alpha, and this is positive 2txy cosine alpha. So adding these two together gives us 0. So it just goes away, and this is what we're left with xa squared plus yb squared. Now, what I want is I want c to pop in this equation, right? I have the t squared in my equation, and I have the xy, right? I have t squared, and I have xy floating here, right? Well, notice from the picture, I know that x plus y is c. It's that entire bottom, right? So x plus y is c. So notice here, so this implies that xa squared plus yb squared is equal to, in this I can factor out a t squared, so I'm going to write it like this, x plus y, t squared, factoring out that t squared, plus, and in this I can factor out an xy, right? If I factor out an xy from both these terms, I would be left with y over here, and then plus x over here. And like I said before, this implies that xa squared plus yb squared is equal to x plus y is c t squared plus xy, and y plus x is of course the same thing as x plus y, and that is c, right? So I get xa squared plus yb squared is equal to ct squared plus xyc, which is exactly what I wanted. And that is the proof of Stewart's theorem.